Today we'll complete part 3 of solution chapter, unit 2, class 12 science. Okay. So here we are first understand what is the vapor pressure of a liquid solution. When we consider the term liquid solution, mark here we are going to talk about the binary solution. Binary solution means what? Here we'll get two components, one solute component and one solvent component to make the solution. Some point or some fact about this binary solution is here whenever you take a liquid in a closed container means all four boundaries are set, the liquid cannot escape. Okay, so if you have taken some liquid in a closed container, then what happen, some vapor pressure develop, the liquid particle will go to the vapor phase and it will create some vapor pressure above the liquid. That is the first point. Second point, whenever you will be adding some solute in that solvent, what happens, solute will occupy the surface. Okay, you know that vaporization is a surface phenomenon, so some solute will occupy the surface and the vapor pressure will change. Sometime it increase, sometime it decrease. Now when it will increase, if you have taken volatile solute are easily vaporized, so in that case the vapor pressure above the solution will increase. But if you have taken some non-volatile solute, then it will occupy the space but it will not go to the it will occupy the surface space but it will not go to the vapor phase, and hence your vapor pressure will decrease. So depending on the solute, the vapor pressure will change, it might increase or it might decrease. Now solute is of two type. One is your volatile solute, that is easily evaporated, for example your alcohol, then ether, then your petrol. Okay, non-volatile solutes are sugar. When you dissolve sugar, sugars are not volatile, so they will not go to the vapor phase. Then salt, etc. Now solute, whenever you are adding in the liquid, it is of three type: solid, liquid and gas. So gas and liquid interaction we have studied in Henry's law, so that we are not going to repeat here. So here in terms of solute we are going to focus basically about the solid solute and liquid solute, and moreover the emphasis will be on the liquid solute. Okay, now so where we'll be considering the solid liquid solution and liquid liquid binary solution. Next, Raoult's law. Let's understand what is that Raoult's law. The law is very simple. Let's start with the liquid solvent. Okay, so in the container we have taken some pure solvent. Now when it is a liquid, obviously it is a volatile. Okay, so it is a volatile, pure volatile solvent. So this is the liquid phase. Here from the molecule will go to the vapor phase. Now when they are in the vapor phase, they will create a vapor pressure. Let's the vapor pressure of this pure volatile solvent component be P1 naught. The naught is for the pure state. Okay, this naught is given for the pure state. So here we got the vapor pressure of pure volatile solvent to be P1 naught. Same way we'll take the solute. So we have taken some pure volatile solute. So the vapor pressure for this solute will be P2. We have considered it to be P2. It is for the pure state, so it will be P2 naught. So vapor P2 naught is what? It is the vapor pressure of the pure solute, right? So here 2 points you see, since both are volatile, they will create vapor pressure. Solute is also, we have taken volatile, solvent is also volatile, so vapor pressure will be created. Now we have considered the vapor pressure for pure component be P1 naught and P2 naught at equilibrium. Vapor pressure whenever it get created, they are in the equilibrium. Okay, some particle will go to the vapor phase, then they will collide and they will come back. So equilibrium established, and at that point we have considered their vapor pressure. So that part is clear. Now next what we'll do, we'll make a solution using this volatile solute and solvent. So suppose we have taken 90 ml of this pure volatile solvent and in a beaker, and we have added 10 ml of pure volatile solute over there. Now whenever we have added this to make the solution, we know what percentage we have taken, so easily we can calculate the mole fraction. We know how much ml of solute we have taken, how much solvent we have taken, so mole fraction can easily be calculated. So that is one thing. Next thing is, as both the component are volatile, there also some partial pressure will be created. Okay, now from solvent, the uh, from this solvent, the molecule will go to the vapor phase and they will create the partial pressure, and we have considered that partial pressure to be P1 naught. Sorry, P1, not only P1. And from solute particle, the one that creates the vapor pressure, we consider the vapor pressure of that to be P2. Okay, so what we got in the solution, we got the partial vapor pressure for the component. So let the partial pressure of the component in the solution be P1 and P2. P1 for the solvent, P2 for the solute. And as I told you, we can also calculate the mole fraction of each component and let it be x1 and x2 for the solvent and solute respectively. Okay, so this two things we got in the solution. So what we got in the solution? We got the partial pressure, because here we can't get the complete pressure because it's a part. Okay, so we get the partial pressure for solvent and solute in the solution, and also we know the, or we can easily calculate the mole fraction of the component. So that much is the thing. Now Raoult says that P1 is directly proportional to x1. Now what is that P1? P1 is the partial pressure of the solvent, that is proportional to the mole fraction of the solvent, that how much amount of solvent is there in the solution, that will determine the partial pressure of the solvent in the solution. Now if you had given more solvent, the partial pressure exerted by the solvent in the vapor phase will be more. If you have added less amount of solvent, then the pressure will be lesser. Okay, so that is one thing. So P1 is directly proportional to mole fraction. Same way for the solute also the same law hold. P2 is directly proportional to x2. Now to remove the proportionality sign and to get the exact value, the the vapor pressure of the pure state, okay, the vapor pressure of the pure state of the solvent is multiplied with the mole fraction. So you have removed the proportionality sign with this P1 naught. And what is that P1 naught? It is nothing but this one, in the pure state, the vapor pressure of the component in the pure state. Okay, so same way for P2, what you get P2 naught into x2. So that is, this is your Raoult's law. So Raoult's law say what? It says partial pressure of component in a solution in vapor phase is P1 naught into mole fraction x1. Okay, it is the product of partial pressure of the uh, entity, solute or solvent, into the mole fraction. Okay, so that is the partial pressure. Next, now once we get the partial pressure of the component, here you see we got the partial pressure of the solvent and partial pressure of the solute. So once we get the partial pressure of the component, that is solute and solvent, we can also calculate the total pressure of the solution. Now let's see how to get the total pressure, total vapor pressure of the solution. For that we have to follow the Dalton's law. Now we know the Dalton's law of partial pressure is total pressure over a solution is equal to sum of all partial pressure. Okay, if you need the total pressure of over a solution, then what you have to do, you have to take the summation of all the partial pressure. Okay, so P total is equal to P1 plus P2. Only P1 and P2, it is limited to P2 because we have taken binary solution, so we just get two component, so we have to add the partial pressure of this two component. Now we know that P1 is equal to what? P1 is equal to P1 naught x1 and P2 is equal to P2 naught x2, right? For binary solution, mole fraction of all the component will be equal to 1, so x1 plus x2 is equal to 1. So hence you can derive x1 and x2 just by subtracting from 1, right? So we had taken here x1 is equal to 1 minus x2, just simplification. Now if you replace this x1 with x2, what you get? You get P total is equal to P1 plus x2 into P2 minus P1 naught. Same way, if you replace x2 Okay, if you replace x2 in terms of x1, then what you get? You get P total is equal to P2 naught plus x1 into P1 naught minus P2 naught. Now one thing you mark here, this P1 naught and P2 naught are constant because these are the vapor pressure for a pure state. Now pure state will always be same. There is no change in the composition, so their values also remain constant. So what you get here is, we have seen that P total, okay, it depend on only one component's mole fraction, okay, either x2 or x1. You can actually express it in terms of only one component. So total pressure depends on only one component's mole fraction, so that we can conclude from this derivation. Okay, so that is the thing. So three conclusions come from this Dalton's law. So what we derived, we just have derived that P total is equal to P1 naught plus P1 naught minus P2 into x2. Okay, let it be equation 1. Now from this equation, the first conclusion come as total vapor pressure over solution can be related to any one component. Here you are getting x2, same way you can give it as x1. So total vapor pressure depend only on mole fraction of one component. Okay, it can be given. Okay, it's not necessary that it only depend on this, but you can express it like that. Next, this equation 1, okay, you can it is very much similar with a linear equation that is equal to y, that is y equal to mx plus c. So here you see P total, okay, y equal to mx plus c, and your equation is P total is equal to P1 naught minus P2 naught into x2 plus P1 naught. M and c are constant, same as P1 P2. Okay, so this equation is same as y equal to mx plus c, which is a linear equation. So what you can say? You can say that P total, okay, that is total vapor pressure over a solution, varies linearly with the mole fraction of any one of the component. Okay, P total, y varies linearly with x, so P total varies linearly with the mole fraction of any one of the component. So that is our second conclusion. Third conclusion is what? Third conclusion say that depending on the vapor pressure of pure component, okay, now pure component, in the equation you see P1 minus P2, the value may be positive or it may be negative. Okay, so if it is positive, P total will increase. If it is negative, it will decrease. So total pressure, okay, total vapor pressure will depend on the pure component vapor pressure, and will increase or decrease with the mole fraction because it is getting multiplied. So if it increase, the mole fraction will increase and P total will increase. If it is minus, if the value come as minus, then with mole fraction it will decrease. So depending on vapor pressure of pure component P1 minus P2 naught, total vapor pressure increase or decrease with the mole fraction. So these are the three conclusions. If you might be asked that what is the conclusion of Raoult's law, so these are the three conclusion of Raoult's law. Okay, now see the graph here. So what we got PT is equal to P1 plus P2 or PA plus PV, and you just learned that this is a linear equation. So see, it's varying as a linear, in a linear form. Okay, vapor pressure versus versus mole fraction you have kept. Now when the mole fraction of the first component is high, is equal to 1, and for the other component is 0, then what happen? If mole fraction increase, you know that the vapor pressure also increase. More is the amount of the substance, more is the pressure, so the value is high. As you are decreasing, okay, see mole fraction of the first component is becoming 0, so their pressure, their vapor pressure also decrease slowly. Same for the second component. For the second component, the value is 1 here, and on the left hand side you are getting the value 0. So if the mole fraction of the second component is high, the pressure will be high, and with the decreasing mole fraction, their value also gradually goes down. So that is the diagram for the Raoult's law. So that's all for today. Thank you.